Okay, so let's see why we need a special rule for taking the product of two functions by looking at this function. So f of x is the product of two functions, x squared plus 1 and x squared minus 1. And we know that we can multiply f of x out and get this, and that we can take the derivative of that very easily using the power rule we just obtained on the previous video for x cubed for this term, and this next term has derivative 0. So here's the derivative of our f of x. But what if we had not multiplied it out and we had assumed that it was okay to take the derivative of the function f of x by taking the derivative of the first factor and getting 2x plus 0, and the second factor, which also has derivative 2x plus 0, and multiplying them together, then we would have gotten 4x squared. And it's clear that this cannot be correct, because what we did over here was legitimate. We used algebra correctly to get this new version of f of x, and we applied the power rule here. So what we need is a rule for finding how we take derivatives of product functions, and clearly the derivative is not. So clearly, or I hope it's clear from the example that we just did right here, the derivative is not f prime of x times g prime of x. So let's see what the rule really is. So we're going to define a function capital H of x to be the product of two functions f and g. The derivative h prime of x is going to be using the limit definition of the derivative h of x plus h minus h of x over h. And if we apply that to the product fg, we get f of x plus h times g of x plus h minus f of x g of x. So as we've seen many times before, when we have an h in the denominator that's going to 0, we have to find some way of pairing that up with an h in the numerator so we can get rid of the h in the denominator. We're actually not able to do that in this case. We're going to need to do a little what mathematicians call trick to figure out a way to handle that h in the denominator. So we're going to rewrite h prime of x this way. So we have written the line above this in this way, and what we've done is we've inserted this term, and we've made the expression whose limit we're trying to find more complicated. But first let's note that when we combine these two terms, they equal 0. And then let's note that, as we'll see on the next slide, that if we group these two terms in the numerator together and then these two terms in the numerator together, we're going to be able to get to a place where we're going to be able to resolve the limit that has the h in the denominator. So we're going to split this expression into two expressions by grouping the numerator here and here, and we're going to think of the numerator as being of this structure, a plus b over c, and we're going to split it into these two fractions. So this fraction here is the a over b, and this fraction here is the b over c. And this is the same as the previous limit, it's just in a different form. So what we want to notice about this limit, or these two limits written in this form, is that the first one has a g of x plus h common to the two terms in the numerator, and the second one has an f of x common to the two terms in the numerator. So we're going to rewrite these two limit expressions factoring out the g of x plus h in the first expression, or the first limit, and factoring out the f of x in the second limit. So when we split about split this limit, or rewrite this limit factoring out the g of x plus h, we write it in this form. Notice that what we're actually doing is it would have been an expression of this form, a times b, or a times b over c, but we're rewriting it as this expression. So this limit here becomes this limit, and this limit here becomes this limit. And now we're actually right where we want to be. On the next step we can actually get a result, but it's not so obvious. So let's take a look. As h goes to 0, we're able to use a rule for limits that says the limit of a product is the product of the limits. So we're able to calculate this limit, or the limit of this expression and this expression separately. So as h goes to 0, g of x plus h goes to g of x. And over here on this second limit, the f of x in front doesn't even have an h in it, so it's just going to f of x. Now what are we going to do with the limit as h goes to 0 of this expression and this expression? This is the crux of this derivation. Well, we should recognize that this fraction here is the fraction that as we let h go to 0, it's the limit as h goes to 0 of f of x plus h minus f of x over h. That's the definition of f prime of x, so we're going to write it that way. So it goes to f prime of x. And what are we going to do with this expression right here? Well, that's just the limit as h goes to 0 of g of x plus h minus g of x over h, and that's g prime of x. So let's put this on the next slide, summarizing what we've obtained. So with our h of x being the product of two functions, f and g, the derivative is the first function times the derivative of the second plus the second function times the derivative of the first. I actually like to write it that way. I think it's easier to understand. Right, so if we write h of x as a first function times a second function, the derivative is the first times the derivative of the second plus the derivative of the first times the second. So you're probably thinking, well, that's kind of a pain, because I could take this original product function and we were able to rewrite it as x to the fourth minus 1, and then it was very simple to calculate its derivative. But what would happen if the function h of x was this? Then multiplying h of x out would be very time consuming, and there'd be a big chance for making an error. So while we wouldn't necessarily use the product rule for this original function f of x, just copy that over, s prime 2x plus f s prime, which would be x squared plus 1 times 2x. Right, so f s prime is here and f prime s is here, and then if we multiply everything out and collect terms, we see that we get the result. But certainly in a case like this, it's easier to multiply the function out and take the derivative that way. Generally the product rule wouldn't be used in this case, but we would want to use the product rule if our function was something like this. So let's go ahead and calculate j prime of x. So we've got f and s prime, and notice that in the s prime we've taken the derivative of this term, bringing the power down, and when we reduce the power by 1, it goes from -2 to -3. And then we've got our f prime here and our s here. We could multiply these two products out, but typically we won't want to do that except in certain special cases. So summing up, here's our product rule for a function that is the product of two functions f and s. It is the first times the derivative of the second plus the derivative of the first times the second. When we have a function like this, we probably would be better served to just multiply the function out rather than use the product rule. But when we have a complex product, such as in this example, the product rule is much more desirable to use than multiplying the function out. Let's also develop a rule for the derivative of quotients of functions. If our function j of x is numerator divided by denominator, our j prime of x is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the denominator squared. So in words, denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the denominator squared. And that's an easy way to remember it using those words, that phrasing. So typically we would use the quotient rule to take the derivative of a rational function. So let's do that here and find j prime. So here we've got the denominator times the derivative of the numerator, and we've subtracted the numerator times the derivative of the denominator, and we've divided by the denominator squared. This one is relatively easy to simplify, so let's go ahead and do that. So we've resolved the numerator into x minus 2 minus the expression x plus 1. The x's cancel out, and we are left with just minus 3 in the numerator. And we wind up with this expression for the derivative of j. I'll make one more note about this function j's derivative. Notice that the numerator is always less than 0 because there's no x values in it, and the denominator being squared is always positive, and so we have a negative number over a positive number, and that means that j prime of x is always negative. So what happens when a derivative is always negative? When a derivative is always negative, that means the slope is always negative, and that means the function is always decreasing. So in this case, we haven't just calculated the derivative, but we've applied it, and we found out quite a bit about this function. We have a function that's always decreasing. So here's a graph of the function x plus 1 over x minus 2, and we can see that both sections of it on either side of the vertical asymptote are decreasing, and that the function is always decreasing. On the final slide, let's sum up what we've learned in the past two videos. So we had the product rule, f prime of x is n x to the n minus 1. The product rule, f s prime plus f prime s, and the quotient rule, d n prime minus n d prime over d squared. One final thing on this video, let's do an example where we combine the product rule and the quotient rule. So let's notice that this function f of x is overall a quotient, and that it has in its numerator a product. So we're going to apply the quotient rule as the overarching rule and the product rule within. So I've set up to show that we are using the quotient rule, and I've left a big space for n prime because that's going to be the product rule, and then we just follow the quotient rule after that. So let's see what happens. So we've got the denominator right here. In taking the derivative of the numerator, we're using the product rule, so it is f s prime minus f prime, plus f prime s, and then the other part of the quotient rule in the numerator is minus the numerator times the derivative of the denominator, and then we have to multiply or divide by the denominator squared, which is right here. So I'm not going to simplify this. This is just an example to show how we use one rule, one derivative rule within another derivative rule. In subsequent videos, we're going to develop some more derivative rules for a little bit more complex types of functions. And that will include trigonometric functions and functions that we can't express in the f of x equals form, and so we have to develop a whole new framework for finding derivatives of those types of functions.